All right, so first 14. Um, so with all these 3D problems, if it shows a coordinate system like that, it's usually a reasonably good place to put your origin and a reasonably good place also to choose your about point. Even if it's not a great place to choose your about point, if you're having to calculate these coordinates, the coordinates of all these points, you might as well make the origin your about point so you don't have to do subtractions and stuff for your row vectors. So I'm going to put my, or I'm going to, just like it suggests, I'm going to put my origin there. And I'm also going to put my row vector there. Um, and so let's come up with coordinates for these points first. A is the origin. B is just 60, 0, 0, just straight out 60 inches in the x direction. C is 60 in x, 0 in y, and 30 in the negative z. D is just 25 in the positive z. E is just 25 in the positive y. F, from the origin, you have to go 25 in the positive y and then 30 in the negative z. G, you have to go 60 in the positive x and then 15 in the negative z. Okay, and that's all the points we need. So let's start filling out a table.
Should F be minus 30? Isn't it
F,
going backwards? Isn't it?
yeah, you're right. Thank you. Right. Okay, so free body diagram now. We have three separate cables. Um, there, there, and there. Uh, I'll call these T1, T2, and T3. And then we have the ball and socket joint. That allows no translation, but any rotations. So that's just three force components. So I'll call this the R vector. And then we have a downward force of 500 pounds. So how many variables do we have? Three for the force, one for each cable, so six. So we're hoping to get six good equations. When I say good equations, I mean ones that aren't linear multiples of other ones or ones that end up being 0 equals 0. So rho, force, moment, um, the force R, that's at our about point, so the rho vector is 0. The forces are X, R, Y, R, Z. Cross product is 0. Then the 500 Newton force, that acts at G. So the row vector is 60, 0, negative 15.
Professor?
Yeah.
If we took the units in inches and just converted them to feet, and our answer is like a little bit changed because of that, is that fine?
Yeah, the answer won't be changed at all. I mean, yeah, I mean, that works perfectly well. And you'll still, since you're still using pound values, it'll all be the same. Your table will look different.
For this one, we would need to, if we wanted to, like from the results, if we wanted to find the foot pounds, we would need to divide it by 12.
Yeah, that's right. But since none of these answers are going to be in units of torque, of units of moment, they're all just forces, 3 components of force for the joint and forces for each of those cables. So your answers will come out exactly the same.
Oh,
Yep. Okay, so we got the row vector. The force vector is in the negative y, so 0, negative 500, 0. The cross product is negative 7,500, 0, negative 30,000. And now we have to do the cables. I'll start with T1. That acts at the point B. So our row vector is 60, 0, 0. Now we have to figure out some stuff about the direction. So a vector that's in the direction of that force, but it's not a unit vector yet, so it's just a vector, is d minus b. So that is 0, 0, 25 minus 60, 0, 0. And so that's negative 60, 0, positive 25. And so the unit vector is negative 0.923, 0, positive 0.385. And so the force vector is negative 0.923 T1, 0, positive 0.385 T1. And so the cross product is 0, negative 23.10. Then T2 the vector in the direction we want is E minus B. So 0, 25, 0 minus 60, 0, 0 is negative 60, positive 25, 0. And so the unit vector in that direction is negative 0.923, 0.385, 0. Guess I should have seen that one. It acts again at that same point B, so the row vector is 60, 0, 0 again. The force is negative 0.923 T2, positive 0.385 T2, 0. And so the cross product is 0, 0, 23.1. And this should be multiplied by T2. And I forgot that on the one above. That should also be multiplied by T2.
T1.
T1, yeah. And then the last one is T3. And that is acting at the point C. So the row vector is 60, 0, negative 30. The force vector. So here's a vector in the right direction. It would be F minus C. So that's 0, 25, negative 30. Minus 60, 0, negative 30. So that's 60, negative 60, 25, 0. Oh, well, that's the same direction as T2. You can sort of see that if you just look at the picture. And so that unit vector is going to be the same as it was for T2, which negative 0.923, positive 0.385, 0. So this is negative 0.923 T3, positive 0.385 T3, 0. And the cross product is 0, 0, 23. Oh, it's not as obvious this time. So I'm going to do that on my calculator. And we get 11.55, 27.69, 23.1. All of these are multiplied by T3. Okay, well, we had six variables. You can see that from the free body diagram. when we add these up, there aren't any components of the 6 Newton's laws that are going to say 0 equals 0. So we get 6 variables, 6 good equations, and we can solve it. Okay. So 6 variables, 6 equations, and so you can solve it. Okay, let's just stop this one there and go to the next one, number 15. That one is a little different than the other ones. All right, so notice that in this one, there's 2 pin joints on this. And the moments on this are not going to add up to 0, which means that, there's nothing to keep that shaft from rotating, and there's moments to make it rotate. So this thing is going to be rotating. Okay, so one of those axes of the moment equation is not going to give you 0 equal, you're not going to be able to set it equal to 0. Okay, so like, notice that this thing, it's free to rotate around the x-axis. Okay, and these moments aren't going to add up to be 0. So this thing is just doing its thing around the x-axis. We can't set that one equal to 0. Okay, and so what we're going to do is just set all the other ones equal to 0 and just not worry about, what's happening with the rotation. Okay, that rotation is designed, like, this thing is designed to rotate like that. We want to use statics to calculate the other forces. Okay, so start with a free body diagram.
Professor?
Yeah.
Would it be possible to have moment on the z-axis?
The z-axis, yes.
But C and D could not do anything about it?
Okay, so here's how it works with so you're right that we're not going to put the couples in the equations. But remember that what a couple is an equal and opposite force. So imagine first that this thing was just like this. So you had this one joint, and you're asking a lot out of this joint, but, it's just doing. So it's supporting it like this. Okay, that's not a great design, but. So in this case, that thing would apply couples that would keep this from rotating, And how would it do that? Well, what it would do is it would apply a force over on this side up and a force on this side down, okay? And that's how it would apply that couple, okay? But now, in this setting, it doesn't have to do that inside itself. It can just apply an upward force here and a downward force here. Those can be a lot smaller to produce the same moment. And so the joints themselves don't have to apply couples because the pair of joints working together can apply those couples. So that's how it works. It's not like no couples are applied. They're just not applied by the individual joints.
So are C and D like 3D? So they have X, Y, and Z?
One of them, I guess, we'd have to choose which one we're going to put thrust on. I think it's not going to matter in this case because there's no forces along the shaft,
Okay, because I had like a Z moment and it wasn't.
Okay, well, let's do it and see. Question?
Yeah, so you just said it, that you said you were gonna decide which one you were gonna apply thrust or not, like, how do we know that, like?
Well, in any problem that I give you,
It will say,
it will either say or thrust won't come into the problem. This is one where I think thrust just doesn't come into the problem, and that's why I didn't say.
okay, so if the question didn't say anything, then we have to know thrust for anything joint.
Yeah.
Okay.
Yep. And if it's on a test and that happens, just come ask me about it if it doesn't seem to make sense when you get your answers. Okay, so free body diagram. So we have the shaft. We have that first gear. The second gear. And we have a downward force of 96. Horizontal force of 265. And here we have horizontal force of 192. And a vertical force of 530. And now we have to think about the joints. So I'm going to assume that there's no thrust anywhere. So at C, we're going to have a force component that way and a force component that way. No force component along the axis. So I'll call this RC. What are the directions? This would be Z. And then RCY. And then at that second joint, we have the same kind of thing going on. This is RDZ and RDY. Okay, any questions? So now we can go to the table. I'm going to use their origin, and I'm also going to use that as the about point. So that's my about point. So for the force vector RC, the row vector is 0. The force is 0 RCY RCZ. Moment is 0. Then we'll go to the big gear. That force is going to be applied at 4 inches in the positive X. And then the radius of that gear 1.5. And so we'd go 1.5 in the positive y. So 4, 1.50 is the row vector. This is gear 1. Okay, now what about the forces? I'm going to just, since these forces are acting at the same spot, I'm going to just lump them into a single force vector. As long as forces are acting at the same location, you can add them together. Okay, so this is going to be 0 for y, positive 265 for z, negative 96 for y. So 0, negative 96, 265. And you get 397.5, negative 1060, negative 384. And then we'll go to that second hinge joint, so RD. Those forces are acting just at 7 in the positive x. So 7, 0, 0. The force vector is 0, RDY, RDZ. Oh, let's see. I'm going to do this by hand. So we got 0 for x. For y, we have negative 7 RDZ. For z, we have positive 7 RDY. And then the last one is gear 2. The location of that force is 9 in the positive x, and then 0.5 in the positive z. So 9, 0, 0.5 is the row vector. The force vector is 530 in y, negative 192 in z. So 0, 530, negative 192. And you get negative 265, 1728, 4770. Okay. Well, since this thing can move freely, about the x-axis, so we're just going to ignore the x moment equation. Okay, so we're just going to skip all of these. This setup is just going to do its thing about that axis, okay? And we're going to calculate all the other stuff. Anybody have any questions about that, the thought process there?
Yeah.
Yeah.
So you would just make all of those 0 because.
I'm not making them 0. I'm just not using that equation.
Okay.
Okay? Because what we would get if we set all these moments equal to, added these up and set them equal to 0, we'd get some number is equal to 0. That obviously is impossible. But the thing is that what those moments are doing is making this spin. So it's around that x-axis, this thing isn't in static equilibrium. Okay, but everywhere else it's still in static equilibrium. So we're just going to look at the other stuff and we're going to ignore the stuff that's not in static equilibrium. Yes?
Well, and we only have 4 variables, so we only need 4 equations.
1, 2, 3, 4. That's right. Yeah. So let's look also and see what else is going to go away. One other one has to go away. And that is, well, these are all equal to 0. So that's going to give us an equation that just says 0 equals 0. Okay. So,
I don't know if it's directing on the x-axis, and there's currently a non-zero moment on the x-axis as well.
yeah, right. So Newton's second law. Let's just put all these together. So we got 0 RCY RCZ plus 0 negative 96 265 plus 0 RDY RDZ plus 0 530 negative 192 is equal to zeros. And we're going to get rid of this equation. And then the moment equation says 0, 0, 0 plus 397.5 negative 1060 negative 384 plus 0 negative 7 RDZ plus, no, not plus, 0, 7 RDZ, negative 7 RDZ, positive 7 RDY, plus negative 265, 1728, 4770 is equal to zeros. And this time we have this equation that's just not in static equilibrium, so we're just ignoring that.
You have no variables in that equation either.
Mm-hmm. And so now our equations, we just have 4 of them. They say RCY plus RDY is equal to negative 434. Then the second equation says RCZ plus RDZ is equal to negative 73. Then our third equation says negative 7 RDZ is equal to negative 6 668. And then the fourth equation says 7RDY is equal to negative 4386. Okay, so we have 4 equations for 4 variables. These are our 4 equations. Our variables, let's go RCY, RCZ, RDY, RDZ, and the constants. So the first equation, RCYs, we have 1. RDYs, we have 1. Constant is negative 434. Second equation, RCZs, we have 1. RDZs, we have 1. Constant is negative 73. Third equation, RDZs, we have negative 7. Constant is negative 668. And the fourth one, RDYs, we have 7. Constant is negative 4386. Okay, and so what I get is RC has no x component, 192.6 for a y component, negative 168.4 for a z component, and RD has nothing for an x component, negative 626.6 for a y component, and positive 95.4 for a z component. Any questions about that? Yes?
Couldn't you add a rotational couple around the x-axis to force the moment in the x-axis?
Well, it's not really here in that case, so it would give you like an answer that didn't mean anything, you know. I would just say spot any axes of rotation where it's not in static equilibrium and just eliminate that equation. Remember that every equation corresponds to a degree of freedom, you know. So if this thing, 1 degree of freedom, isn't in static equilibrium, then that static equilibrium equation just doesn't mean anything. Okay, that's how I would think about it. Okay, let's do the quiz.